When it comes to complex reasoning in AI, the go-to strategy for a long time has been pretty simple. Just think longer. Extend the chain of thought, pile on more steps, and just hope you land on the right answer. But what happens when you just hit a brick wall? When a problem doesn't need more steps, it needs a totally different approach. Okay, let's get into this, because a new paper from Microsoft Research is proposing a huge shift. What if we could actually teach models to think smart?
And this quote from the paper, it just nails the mission. This isn't about more brute force. It's about cultivating something much deeper, advanced cognitive abilities. We're talking about the ability to use tools, to actually reflect on feedback, and to autonomously change course when things go wrong. This is the whole idea behind the rStar2-Agent, and we're going to unpack exactly how they pulled it off.
So, here's our game plan. We'll kick things off by understanding why current methods hit a wall. Then, we'll check out the beastly infrastructure they built to tear that wall down. We'll get right into the weeds with the core algorithm, GRPO-RoC, see the super efficient training recipe, and then the results. Finally, we'll take a little peek inside the mind of this new kind of AI.
All right, so let's start with that wall. Current methods, the ones that just extend the chain of thought, or COT, they're powerful, sure, but they're also kind of brittle. They really struggle with tiny errors buried deep inside a long line of reasoning. And if that initial idea is flawed, they often can't self-correct. They just keep digging the same wrong hole, making for a longer, more spectacular failure.
This slide really breaks down the paradigm shift. Thinking longer is basically a monologue. The model is just talking to itself. But thinking smarter, the way rStar2-Agent does it, that's a dialogue. The agent doesn't just think in a vacuum, it acts. It uses a Python interpreter as a tool to test its ideas, to verify its steps along the way. And, this is crucial, it gets feedback from that environment. A code error isn't a dead end. It's a signal. It's a chance to learn and adapt.
Of course, giving an AI this kind of interactive ability, especially at scale, is a massive engineering problem. You can't just hook up a Python interpreter to a language model and hope for the best. Nope, you need an engine built for the job.
And this diagram just beautifully shows their solution. The researchers were staring down two huge bottlenecks. First, a single training step could unleash tens of thousands of tool calls all at once. Their solution? An isolated, high-throughput code environment that can handle a staggering 45,000 concurrent calls, with an average latency of just 0.3 seconds. Insane. Second, these agent rollouts have wildly different lengths, which just wastes GPU time. So they built a load balance scheduler that dynamically juggles the work, squeezing every drop of efficiency out of the hardware.
Okay, so we've got the concept, we've got the engine, but how do you actually get the agent to learn from all this interaction effectively? Well, that brings us to the core algorithmic magic of this paper, a whole new way to teach an agent to learn from what it does.
Here's the problem. If you just use standard reinforcement learning, the model gets stuck in a rut. It develops bad habits. This chart here shows the rate of tool call errors, even in trajectories that still manage to get the right answer. See that purple line for standard RL? It just flatlines. The model learns that making a bunch of messy mistakes along the way is totally fine as long as the final answer is right. So, why does that happen?
The problem is something the paper calls environment noise. All those little tool errors, syntax mistakes, timeouts, flawed logic, they create a ton of distracting feedback. Since the reward is only based on the final answer, the model never gets a clear signal to avoid these messy, inefficient paths. It basically learns that sloppy work is okay, which leads to these super long, low-quality solutions.
The solution is just so elegant. Resample on correct, or RoC. Instead of trying to penalize bad behavior, you just amplify the good stuff. The process is really straightforward. First, you generate way more potential solutions, or rollouts, than you need, say twice as many. Then, for all the ones that got the right answer, you filter them, keeping only the cleanest, most direct paths with the fewest tool errors. Finally, you just take a random sample from the failed paths, so the model still learns from a wide range of mistakes. It's this clever asymmetric strategy that cleans the training data on the fly.
And this is the objective function that powers the whole thing. Let's quickly break this down. The model's goal is to maximize this function J. Now, the absolutely critical part is right here. It's not learning from all the possible paths, but only from A. Those are the super clean, high-quality paths that we handpicked using our resample on correct strategy. The AT term here is the advantage, which basically tells the model how much better a specific action was compared to the average.
By calculating this advantage only on the best of the best examples, we're explicitly telling the model ignore all that noisy, inefficient stuff and focus only on replicating these elegant solutions. So we're not just filtering data, we're fundamentally reshaping the learning gradient itself.
Now, this powerful algorithm gets paired with a training recipe that is just shockingly efficient. This isn't just about a new algorithm, it's a whole new philosophy for how you should train these reasoning agents right from the very beginning.
So, unlike a lot of other approaches that start by fine-tuning the model on tons of reasoning examples, this recipe does the exact opposite. It kicks off with a non-reasoning supervised fine-tuning stage. The only goal here is to teach the model basic grammar, how to follow an instruction, and how to format a tool call. That's it. This stops the model from getting stuck on specific reasoning patterns and, this is key, it keeps its initial answers short. This lets the reinforcement learning do the real heavy lifting of cultivating actual reasoning ability.
The reinforcement learning process itself is this really clever, staged curriculum. It starts with a wide range of problems and a pretty tight token limit, forcing the model to learn efficiency from day one. Then, as it gets better and starts bumping up against that limit, they increase the token length. Finally, in stage 3, they filter the data to focus only on the hardest problems, the ones the model still messes up, to really push it to the edge of its capabilities.
And the result of this whole sophisticated recipe, it comes down to this one number, 510. That's it. That is the total number of reinforcement learning training steps it takes to get to state-of-the-art performance. Just let that sink in for a second. In a field where models often train for weeks on thousands of GPUs, this approach gets to the finish line in just 510 steps. This kind of efficiency completely changes the economics of building these powerful agents.
Okay, so it's incredibly efficient, but is it any good? Let's get to the results, because this is where the story gets truly compelling. How does this relatively tiny 14 billion parameter model stack up against the absolute giants of the industry?
I mean, this learning curve really says it all. That green line is the 14 billion parameter rStar2 agent. The purple line, that's DeepSeek R10, a model more than 45 times its size. Just look at the speed. Within a few hundred training steps, rStar2 doesn't just catch up, it blows right past the much larger model on the AMI-24 benchmark. This is just a stunning picture of what training efficiency and raw power looks like.
And here are the final scores. On the super challenging AMI-24 math competition benchmark, the 14B rStar2 agent hits 80.6% accuracy. That's better than heavyweights like the 671B DeepSeek model and even OpenAI's O3 Mini. This isn't just a small model punching above its weight. This is a small model that's not just competing, it's winning.
And this right here, this just drives home the core theme perfectly. How is it doing this? By thinking smarter, not longer. Look at the average response length. As a rStar2 agent is getting these top-tier results while using thousands of fewer tokens than its competition. It's more accurate and more concise. That is the literal definition of efficiency.
Okay, so for our final section, let's move beyond the numbers and the charts for a minute and look at an actual example of this agentic reasoning in action. What does it really look like when a model thinks smarter?
This is a trace from the model's internal monologue right after its Python code failed. Just listen to this. It correctly diagnoses the problem. The error occurred because then it starts brainstorming multiple different fixes. Instead of wrapping the remainder, I can simply check. It even thinks about a completely different backup plan. Alternatively, I could fall back to, this isn't just pattern matching. This is a model reflecting on external feedback and autonomously creating a brand new, successful plan.
And that's what brings us to the final and I think pretty profound question. When we see behavior like this, an agent that can figure out its own mistakes based on what the world tells it, and then come up with new solutions to fix them, are we just looking at a more advanced form of reasoning, or are we starting to see the first real glimmers of something that looks a whole lot more like genuine, in-the-moment learning? That's the question rStar agent leaves us with.